Good afternoon, all. Welcome to this session on 3D vision problems and possibilities by Professor Viswanath. The brief bio of the speaker. So, Dr. Viswanath finished his BTech from National Institute of Technology, Calicut, and received PhD from School of Computer Engineering, Nanyang Technological University, Singapore, in 2011. His PhD topic was focused on building computational models for identifying salient regions in images and videos. From 2011 to 2019, he worked with Samsung Research Institute, Bangalore, on various research topics of interest in areas of computer vision and machine learning. During this period, he was involved in developing and leading efforts towards machine learning-based vision algorithms for Samsung's flagship models, which involved object detection, scene recognition, semantic role recognition, and object and scene segmentation. Since 2020, he is working as a faculty in IIIT-Bangalore. His current research areas of interest are in vision plus language multimodal fusion for 3D scenes, 3D model-driven segmentation, and 6D pose estimation, and generative AI for vision. So it's a pleasure to have you talk today. Welcome to this.
Thanks, Raghuram. And good afternoon, everyone. So the topic for today is 3D vision problems and possibilities. So as the title says, this talk is going to be a more generic talk, discussing what are those important problems to be solved, and what is the future lying ahead when we are considering the recent advancements in deep learning and generative AI. So it will be structured like for a general audience. So I'll start from the very basics of image formation to different problems in 3D vision, and end it with a note on the recent advancements in 3D vision. So let's start from a more familiar topic, that is the 2D vision. So 2D vision is a more familiar topic. So let's discuss the top level objectives in 2D vision. And all of you might be familiar that we try to do image classification, object detection, which is localizing an object into a specific region, semantic segmentation, where the problem is to get the label of every pixel to a semantic category. We have instant segmentation, where the objective is to again to get the label for every pixel, but this time not just the semantic category, but the instance ID of that object. Then we have problems like pose estimation, or we have even the recently we could create 2D images using generative AI techniques. So if you look at the problems of 2D vision, after all, we are talking about the problems where we have captured the image and the image is lying somewhere in the web. And what all things we would like to solve with these 2D images, maybe searching across the web, finding matches, understanding automatically the content of the image, trying to do some intelligence on top of that. But at the end of the day, we are talking about images being stored somewhere. We are not talking about the scenario where the 3D scenario where the images are being captured, where applications demands to know the 3D scene of the capturing environment. So what are those applications that really requires for us to know the 3D scene on which the images are being captured? So let's move on to the 3D vision objective. So the objective of 3D vision is to obtain the understanding of 3D world captured in the form of, so you could capture the 3D world different ways. You can take multiple images of a 3D scene and try to understand the 3D scene, or you could use different kinds of sensors to create a point cloud data of the 3D scene. But assuming that the 3D scene knowledge is there, we have multiple applications in place. So this is an example where I have this object, and I have multiple cameras capturing this object from different angles, and the effectively understanding the 3D structure of the object. So this is the case where I have multiple views to understand the 3D structure. Or I could use point cloud based scene capture, where the point cloud is generated using some kind of time of flight based camera, where you send a laser or you send infrared and measure the time it's rebound back and get the understanding of different depth points. So either way, you understand a 3D scene and what all things you could do with this understanding of 3D scene. So let's look at some of the captivating applications first before getting to see how we go about solving these different problems. So of course, autonomous driving requires understanding of 3D scene for a better judgment of braking and maneuvering systems, right? And we have indoor and outdoor navigation, where you would like an autonomous agent to move inside a building or outside a building, understanding autonomously the 3D scene. Not that somebody is providing it, but with the images being captured, the agent should simultaneously localize and map itself with respect to the 3D. So that's a very important problem to be solved. Then, of course, we are having these days more and more applications emerging in mixed reality and augmented reality, where 3D scene understanding is also the need of the hour. Moving ahead, we have this robotic manipulation applications, where a robotic hand is required to go and grab an object, where you should understand from the robotic, the camera of the robot, where exactly the object is positioned. And this is the 6D pose estimation, where we have to figure out the three displacement at delta x, delta y, delta z, and the three angles of the object frame. So that problem, if you solve this problem, and with the knowledge of a CAD model of the object of interest, we can in fact make the robot manipulate the object. We get a lot of data in terms of 3D point cloud, and again, many times we would like to understand the data labels in the 3D point cloud manner. So just like we have solved semantic segmentation, where we understand the pixel labels in 2D data, a 3D point cloud segmentation might be required when an automatic understanding of a 3D scene is required. Another very recent application is 3D scene creation from a set of 2D images, where this time I'm not going to use explicit scene creation, but I will use a neural network based rendering, where the neural network encodes the implicit information of the scene, and it can render the scene from different camera viewpoints. So these are many of these applications that are somewhat emerging. Not all are solved completely. We have lots of challenges in each and every of these applications. And as we see that the world is moving more towards autonomous agents, robots helping in everyday life, 3D vision is going to get all the more importance, and maybe more than the 2D vision after a point, because you see that most of the problems in 2D vision are getting saturated. We could pretty much understand the content of an image in the semantic sense and all. So understanding 3D world is still more challenging. We don't get a lot of data. We don't have foundation models in 3D. So it's more of an academic problem still, and we are happy about that, because other problems are being driven by industry when we plug in billions of data and build big models. But there are lots of scope to there's a lot of scope in academics in the 3D world still. So let's start from the very basics of vision, and let's move on to discussing more and more complex topic. So let's start with the definition of a camera pinhole model. So most of the times when we mathematically describe the 3D world, we have to assume a camera model. And it suffices that we assume the basic of the basic camera model, which is a pinhole model, for most of our practical purpose. So let's understand what is a pinhole model. So what is the process of an image formation? If you keep a white screen in front of an object, say for a tree, for example, you don't get an image over the screen, right? For what reason? It's because any point you take on the screen, that screen gets rays from the multiple areas, and these rays cancels each other and effectively not forming the image on the screen. While if you take the screen quite close, and if the object is predominantly green, then you might see a green tinge on the white screen, but you still don't see the object on the white screen, right? So how to make sure that the rays falls onto a screen which is not disturbed by the rays from the other sides of the object? So that is where the basic camera pinhole model comes in, where you have a pinhole through which the rays are passing, so effectively forming the image on the screen. So we have the screen over here and a pinhole over here, and you get an inverted image formation when you keep a pinhole model, right? So we have challenges with this model, because we might need a lens for this reason that it depends on the aperture that we use. If my aperture is too large, the color or the image that is formed over here can get blurred, and effectively having a blurred image. Or if I use too small aperture, the problem is the image may be sharper, but you get a darker image because you don't allow too much of light to pass through, right? So either the blurriness or the lack of illumination is a problem with the aperture. So that is where we need a lens, because the lens is the way to collect the rays from different angles from the same point and converge it to a point on your screen. So so we see most cameras come with all cameras come with lens, but when we are building a camera model, we might want to just ignore those distortion effects brought by lens and just stick onto the pinhole model, and still do the math will be serving the same similar, and it does not affect a lot of the applications. It doesn't matter. So let me start talking about the camera projection before going to the 3D world modeling. So in cameras, there are different kinds of cameras, but ideally a camera would like to do what a human eye does, and a human eye sees the object through perspective projection. So that is what we are actually replicating in a camera. But there are other kind of cameras where we want the measurements to be exact. So we have the different kinds of projections like orthographic projections, but perspective projection is the most common kind of projections that we see on cameras. So what is a perspective projection? So a perspective projection is what we have just seen that. And in that perspective projection, we assume that the camera is a rigid body. So the camera is basically described by an XY axis. And this X and Y axis is always parallel to your image plane. And its origin is always centered on the pinhole of the camera. And there is an Z axis that is perpendicular to the image plane. So that's the fundamental assumption you take. So to understand a camera motion, now it's a matter of understand how the camera axis is moving. We can just forget about the camera image as such, and you can just think of an axis in 3D that's moving, and always the XY axis, the camera screen will be there, and Z axis is the axis to which the camera is pointing on to, right? So we have just abstracted the camera to an axis. So now I can represent the camera movement as rotation and translation of the camera axis. Now, if you look at the image formation in a camera, you can see that if I have an image in 3 dimensions, if I have a point, for example, in 3 dimensions, I have to represent this point with respect to some axis, right? So if I say X, Y, Z, it is with respect to some axis. And currently I'm looking at the camera axis. So here is my pinhole, and here is my image plane, and the camera axis is positioned like this. So the Z axis is called as optical axis. And now if I consider a ray starting from this point, passing through the pinhole, it falls onto a position on the image screen. And you say that this is the corresponding 2D point of this 3D point. So this 2D point is always expressed with respect to another coordinate frame, which is the coordinate frame of the image plane. While this 3D point could be expressed with respect to different reference frames, as of now, I have chosen to represent it with respect to the camera frame, right? So this is the problem setting we have for perspective projection. Now, our objective in understanding the 3D world is that we always are provided with this image. So from this image, from this x dash y dash location, I should be understanding where is the original 3D point xyz that has created this x dash y dash location, right? So many times we deal with a virtual image plane, not the actual image plane. So it means that I take this image plane in front of the camera. If it was f distance backward, I just take it f distance in front. So that makes my math easier, because otherwise I have to deal with an inverted image. But if I just take it f in front, I have to just deal with a upright image, while rest of the all math remains the same. So whenever you're seeing literature on 3D vision, you always see this kind of a formulation where you have the x, y, z axis, but the image plane is in fact in front of the camera. That is only to make the math simpler. So we have the object point and we have the pinhole. So once you have the object point and pinhole, what you have to do is just to draw a line from the object point to the pinhole, and it pierces the image plane at one point. And that is the point where the image is formed. So the image plane is taken to front, and no image inversion implies no sign inversion, otherwise the math remains the same. So let's take a look at a 3D to 2D projection scenario. So here is a 3D scene, and here is the camera looking at the 3D scene, and here is my image plane, and here is a point I'm interested in. So this point is represented as xs, ys, zs with respect to this frame, this axis, right? And I have a point getting formed over here, which is my image point, and that image point is expressed as xj, yj, f, where f. So these 2 points are in fact represented in the 3D frame of the camera itself, right? This is z away from the camera, while this is f away from the camera. So f is the focal length, the distance from here to here, right? So that is the z-axis length. So always the focal length is the distance between the pinhole and the screen that you place, right? So the 3D location, if you have to represent in that way, of this 2D image formation point is xj, yj, f. Now, using a basic trigonometry, we have relations governing this set of three, this location and this location. So that can be easily understood by drawing some triangles, and you see that the x location of the point of image formation is related to the original x location and z location and the f by this formula, and the y location, which is again a point on this image formation, is related to this formula. This comes from similarity of triangles. So what it says that I have a 3D point. If I know the focal length of the camera, I can, and if I know where is that exact location of the 3D point in the world with respect to the camera frame, then I can pretty much say where will that point will be forming its image on the camera image plane, right? So that's what this equation tells you. Now, once the image is formed, the camera forms what we call as a projective transformation. So a projective transformation is sometimes tricky because many things looks distorted in a projective transformation. You are starting from an image, and we want to recreate the 3D world from the images we have, but the images itself looks distorted. And what kinds of distortions we have to encounter in the while the camera is forming the image? So let's look at a simple scenario here. I have 3 cameras looking at a window. So they are positioned like this, and this camera sees this area of the room. This camera sees, so I have a window over here, and this camera is seeing the window like this, while this camera looks from here and it sees the window like this, while this camera looks the straight and it sees the window like this. So you see that the three cameras positioned at three different locations in the room, looking at a window which has rectangular parallel lines, it forms the images like this, right? So what all things have remained same if I take the camera from here to here to here? Does the angle between the lines remain the same? Does the parallel lines remain parallel? If you ask these questions, you see that the angles do not remain the same. The angle have changed from here to here. Between these two, also there is a change, right? These angles are changing. While the length is also changing. Even the ratio of the length will change. The ratio of this with respect to this and this with respect to this are changing. So the lengths, angles, ratio of the lengths, everything is changing in perspective projection. So what has not changed? What is the invariant of a perspective projection? If you ask the question, the invariant is in fact lines remains as lines, right? Lines does not become curves. So what are the properties of geometry preserved by perspective projections? If you look at these, none of these are preserved by perspective projection. The shape, angles, distances, ratio of distances, parallel lines, nothing is preserved when you do a perspective projection. And that is how we see the real world, right? We see nearby people taller than the faraway people, they are shorter, right? And while straightness is something that is preserved in a perspective projection. And we have cameras designed to emulate human visual behavior, right? So from that point, we have to see the challenges involved while when we are dealing with these kind of images. So moving ahead, we have to understand a 3D scene. We have different mechanisms to understand. One is that we try to do it with a single camera, taking it around, while the camera will be taking different images of 3D scene. For this, we have to understand the motion of the camera. The camera motion is the motion of a rigid body, right? And this motion is completely specified by the camera axis, right? So we have to understand basically how the camera axis moves in the 3D world. Then we completely describe the camera motion, right? Because the image plane is coupled with the axis, and the direction of where the camera is pointing to is also coupled with the axis, right? So if you just describe the motion of the camera axis, we are describing the camera motion. So to understand the rigid body motion of camera, we have these terminologies. So we keep always two coordinate frames. One is called as the object coordinate frame, or we call it as body coordinate frame, and other is called as the world frame. So if you take an example over here, suppose there is a drone that is flying from a docking station and basically capturing image. You couple a object frame to the drone or drone's camera and see that how that frame is moving with respect to docking station's frame, which is the world frame. So the complete motion of the drone is expressed in terms of its relative position with respect to this world frame, which does not move, right? So how do we represent the camera motion with respect to a world frame? We just need 6 parameters to represent that. And what are those 6 parameters? The 2 components of that is, first is a translation vector, which is the delta x, delta y, delta z, which will take the center to some position over here, right? And then we need 3 more parameters, which is the relative orientation between the axis of the coordinate frames. How much it has turned around x-axis, how much it has turned around y-axis, and how much it has turned around z-axis. Initially, you assume that these axes were aligned and the centers were aligned. From this, it has moved over here with some degree turning around x, some degree turning around y, and some degree turning around this z-axis. So we have this alpha, beta, gamma, different angles, and delta x, delta y, delta z. So if we estimate parameters, we know where the camera is in the 3D, right? So I would like to give a small intuition to the representation of this the 3D position. So let us look at 2D rotation first and then extend it to 3D rotation. So if you are wanting to represent a 2D rotation, example, I have to represent this point has moved over here. This point xy and this point x dash y dash. This point was making an angle over here, and this point was making an angle of theta between these two rays. So if I have to represent the rotation as a matrix operation, it's easier to see that. It is easier to deal it in polar coordinates. So let me represent first xy in polar coordinates as here, and let me represent x dash y dash in polar coordinates as a theta additional angle between from here to here, right? So if I represent them as in polar coordinates, then I can easily expand this cos a plus b, and I can write x dash as an expanded form, right? And similarly, I can expand the y dash as in this form by expanding the sine a plus b. Now I have a relationship governing x and x dash. I can easily see that x dash. Here I have x coming over here, and this is y. So I just replace with the x and y, and similarly I replace the x and y over here also. X replaces this factor, y replaces this factor. So if I replace with the x and y, I have a relationship that is governing x and x dash. So you see that it's a simple matrix operation that basically what we call as the rotation matrix, right? So my rotation matrix is completely governed by a single variable. So the degree of freedom here is just 1, right? If you know the angle theta, you can write the rotation matrix and just govern the relationship between xy and x dash y dash. So that is about the 2D rotations. Now, if you come to 3D rotation, we have to deal it in across 3 angles, which we can which is also termed as yaw, pitch, and roll. So this terminology has come from aerodynamics. So you assume a plane and it's moving in one direction. It has its wings is in one direction, and the vertical direction is there. So you can fit a 3D axis to a plane once you fix the moving direction of the plane. And always the moving direction is called as the roll axis. The vertical axis is called as the yaw axis, and the axis that is parallel to the wing is called as the pitch axis. So if the plane rotates around the roll axis, we call it as a roll on the yaw, and the one that is on the around the wings, it is called as a pitch rotation. So this can be generalized to any object that is in motion. You always call the roll axis as the direction of the movement of the object. So here it is a small vehicle that is moving, and you call this as the roll axis, the vertical as yaw, and the one that is perpendicular to both as the pitch axis. So we have to basically define the rotation in around these 3 different axes. So if I'm looking at the rotation around the yaw axis, what happens is that this x0 y0 will change to x1 y1, right? I'm not changing the basically I'm like this, and I'm just rotating like this, right? So this is represented as a rotation matrix where there is no change in the z angle rotation, while there is some change happening in the xy plane, right? So essentially, if you look at the 3D rotation, I am basically converting it into 2D rotations, which has basically the rotations in different planes: xy plane, yz plane, and xz plane, right? So if you're rotating around your axis, what you're doing in fact is rotating only in the xy plane. If you're rotating around the roll axis, you are only rotating in the yz plane. Similarly, if you're rotating on the pitch axis, that means on the y-axis, you are only rotating in the xz plane. So these 3 matrices represents the rotations that is happening, and a complete rotation is obtained by multiplying these 3 matrices. So your 3D rotation is essentially represented as a product of these rotation matrices, right? So if you are looking at a rotation of a object under 3 different axes, it pretty much looks like this. That means initially you started with 180-degree rotation, then you went at 45-degree rotation, and then you went to a 90-degree rotation. So if you have to say where is a 3D object with respect to a 3D frame, you just specify the rotation matrix, and the rotation matrix has only 3 degrees of freedom. Unlike it may have 9 elements, but you just have to understand what is gamma, beta, and alpha, right? So that is where we said that to know for sure that where is a 3D object in 3D world, we just need 6 parameters, right? The 3 distance parameters, the delta x, delta y, delta z, and these 3 angles, alpha, beta, and gamma. That completely specifies where is the 3D object's frame. And if you know the 3D object shape, then you exactly understand where is the 3D object, right? So coming to the problems now. So we have just very quickly laid the basics of how an image is formed, how do you take a camera in the 3D world, and how do you represent its movement in 3D world with respect to the 3D rotation and 3D translation. Now, what are the kinds of problems that we are trying to solve? So if you look at one of the problem is camera pose estimation. So a camera pose estimation problem is that I want to know how much my camera has moved. This is my world frame. So first I fix my world frame, and from this frame, how much my camera has moved. Now I am looking at a 3D object over here, and I want to understand. I have an image also. So I basically have taken the image of this 3D object, and I want to know how much my camera has moved from here to here. That means I want to estimate the rotation matrix and the translation vector, right? So there are different settings for this problem. One of the setting is that I say that I know the exact 3D locations of this object with respect to the world frame, and I match them to the image formed on the camera. Well, that is not always the case, right? You don't know the exact 3D locations of in an object unless you are calibrating the camera, like as in you have a checkerboard or something, or a cube, where you can assume the world frame is on the corner of your cube, and then the camera has moved and you are taking the photo of the cube. Then you know that exactly that if you assume the world frame is on one corner of the cube, then you can say that yes, this point is 3 left, 3 right, 3 top, something like that. And then you say this point is belonging to this point on my image. So I have a 3D to 2D correspondence. So for camera calibration, we get this exact 3D location using a non-object. That's most important. Using a non-object, you fix your world frame and you make a correspondence from 3D to 2D. So if you know that, so that's the condition. If you know that exact 3D to 2D correspondence, then we can solve for this R and T. That means how much the camera has rotated, the rotation matrix, and how much the camera has translated. There are different methods to do that, and they come under the class of methods what we call as perspective endpoint methods, PNP methods. So that is not always the case. You don't get to have exact 3D locations with respect to a world frame, right? So a more practical case is what we call as the structure from motion problem. So here I am looking at a 3D object, an object in the 3D world, and I am taking photos from different camera locations. Now I don't know these points, how far these points are from the camera axis. What I know is that this image and this image is correlating because there are certain overlapping points between these two images, and this image has some overlapping point with this image, right? So I have a group of image where I can basically find matchings between this group of images, but I have no other access to know the exact 3D location of this object. But then we solve it using a combination of multiple techniques. We first estimate the relative motion between these two camera location, and once you estimate, so that's again using what we call as estimating the fundamental matrix and solving for the relative motion. Once you estimate the relative motion, then you can estimate the 3D location using a technique called as triangulation. So there are multiple steps, as I said. First, you estimate the relative motion, and then you use a triangulation method to estimate the 3D location. So once you have 3D location, well, I will not be satisfied with that estimation because it could be very noisy. So I will use the rest of the views to corroborate my estimation. So that solving for together for complete using the n views and solving for the complete 3D location along with the camera positions, this technique is called as bundle adjustment. So in it's again an optimization problem. So you solve together the camera positions and the 3D locations, because there are multiple corroborating evidences, right? So we have to solve it together instead of looking at a pair at a time. So this can be posed as optimization problem, which could be solved using Newton's method or Gauss-Newton method or Levin-Buckwart method. So but again, the posing of the problem is important here, and what you get is again 3D positions with respect to a world frame. So whenever we say a 3D location, we have to tell it is with respect to some frame. So we usually fix the world frame as the frame of the first camera. So this structure from motion has ignited a lot of interest in the recent years, because there are lots of applications coming out. One of such very interesting applications are you could just take the pictures in the web of a monument taken by different tourists, and then one could take two random pictures and estimate the relative pose between those cameras, and then build the structure of the tourist site from this group of pictures, right? So without even going to the place, from a group of images using this technique, we are rebuilding the 3D structure of the tourist site. So an allied problem that is very important in robotics is simultaneous localization and mapping. So here also we solve this problem using what we call as the bundle adjustment. But it is usually done for navigation purposes. So here the robotic agent is moving in a indoor or outdoor scenario, and it keeps seeing the images, right? So based on the images it's seeing, it should basically localize itself. It should estimate its position and also build a 3D model simultaneously. And that's what we are doing in the bundle adjustment in this structure from motion also. The camera is localizing itself and at the same time building the 3D model, right? So SLAM is an extension of that, and while the applications are different, for structure from motion we are more interested in the structure of the 3D object, while in SLAM we are interested in navigation as the end goal, right? So just to compare the SLAM and structure from motion problem, most of the times SFM, which is structure from motion, is done in an offline mode, while SLAM is a real-time requirement most of the times, because the robot has to maneuver inside an unknown environment. Loop closure is an important aspect here, because unless it closes the loop, it doesn't know the scale and where it started and how it has entered or not. So otherwise, there are lots of similarities. The focus is on 3D reconstruction for SFM, while SLAM, the focus is on localization and the mapping the environment completely. So one of the other problems that is of interest is 6D pose estimation. So here this problem is for robotic grasping. So here I'm assuming that I'm seeing a scene, or rather the robot is seeing a scene, and I would like to grasp the object. So now you know the CAD model of this object of interest. So you assume that this scene is happened in such a way that the CAD model was first aligned and put on the object, exactly on the object, and then it has the frame, the object frame has done a rotation and translation. The camera was also aligned here. Initially you assume that the 3D object was here, the camera was also here, totally aligned. Now the camera has taken a rotation and translation, and it's seeing the object from a certain viewpoint. Now that is what you are seeing over here as an image. Now it becomes a problem of estimating the camera pose again from the world frame, where the world frame is now your CAD model's aligned frame. So if you estimate this R and T of the camera, and if you know the complete CAD model of the object, now the robot, if you assume it's the eye of the robot, now the robot can directly go and grasp with the knowledge of the shape of the model, right? So this is also an important problem to be solved, which we call as the 6D pose estimation. So this is some of the state-of-the-art works here that we are also looking onto some of these problems in our lab as well. So here, yes, what you are seeing is an image basically taken, and we are moving the camera, and the images are replaced with CAD model. The objects are replaced with CAD models, and their pose is every time estimated. So if you have this information, then it makes a case for a much easier case for robotic manipulation of objects. But it is also a very challenging problem, especially on cluttered scenes and cluttered objects. And on a control scenario, on a factory setting, it is much easier. But on a cluttered scenario with occlusions and all, it's a much more difficult problem, and maybe it's an interesting problem to solve, because we need such cluttered, we are facing such cluttered environments. Maybe in the waste segregation scenario, or different scenarios can come up where you might need faster robotic manipulation without human intervention, right? So these are number of problems that you see, and now we are talking about 3D representations, right? So the one way we talked about representing the 3D scene is to take multiple images of using a camera and estimate for the depth of that point, each pixel with respect to the camera frame, and then represent them as points, right? So there are different ways to get 3D data. One way is to use multiple cameras, but we have other sensors as well. So usually we work with first, there are different ways to represent 3D. That is, like point cloud is one way to represent, meshes are another way to represent, so voxels are another way to represent. So there are different ways 3D data could be represented, and we are now talking about point clouds. So point cloud is popular because it is easier to store. So what is a point cloud data? So just like we are storing an image, like an XY location, I have RGB value. Point cloud data stores in XYZ location, I have something. That something could be an RGB value, that could be a surface normal, or some feature representing the object of interest. So I have this long table where I have XYZ, against that I have some RGB or a surface normal value. So, but the difference between an image and point cloud is that image data is structured, right? I have XY as 0, 0, 0, 1, 0, 2, like that. And in the structured grid, I have RGB values coming at in a very structured manner. But in point cloud, we don't have such guarantee. It depends on completely how we are acquiring the data, right? So we may have very sparse points in some area, while we may have dense points coming from some other area. But eventually this is represented like XYZ against that some RGB or surface normal or some other feature value. So point cloud is a set of data points in a 3D coordinate system, and it can be created using you have different ways of creating it. So one way we have seen is the structure from motion. We can use a LiDAR to create a point cloud. We can use an infrared to create a point cloud. We use infrared mostly for what we call as RGBD cameras. Use infrared rays and also capture the RGB value, and that's mostly in the indoor applications, right? Because once you take this camera out, the infrared of sun will obstruct the infrared, and you will not get accurate depth measurements. So infrared cameras or the RGBD cameras are most popular in using the indoor applications like Microsoft Kinect. While for mapping the far regions from top, like drone-based mapping, we have LiDAR-based cameras. So these are laser pulses that is sent, and again time of flight is measured, but this does not get disturbed with the sunlight interfering. So LiDAR is used in the outdoor scenarios, while infrared is quite useful in indoor scenarios. Structure from motion is popular because it doesn't come with a baggage of additional sensor, right? You can use the same camera sensor and just take it around and get a point cloud of the object. So cost-wise, that's the cheapest. Then the RGBD, and then the LiDAR. LiDAR also requires heavy duty. It's heavy in the size also and cost also, and so many times maybe the drones may not be. You need to design drones that are large enough to carry on this heavy sensor. One of the problems with 3D point cloud is again classification and segmentation. We have dedicated deep networks to do point cloud classification and segmentation. One of the key, why do we need a different kind deep neural network here is because the traditional neural networks are sensitive to order arrangement, right? If you are feeding an image and then if you change the order of the pixel, of course the image has changed and it should predict something else if you change the order of the pixel. But when you are presented with a point cloud, nobody is giving you any order. There is no scanning order for a point cloud. I can present the point cloud in any order, right? Yeah, but then the current neural networks are sensitive to the order by which you are presenting the input data. So that required dedicated different kinds of architectural advancements to handle the point cloud data. So PointNet and PointNet++ has been the state of the art in creating point cloud features. So what it means?
Batch data always sorted before the time.
So the point cloud doesn't present itself an order. So I can't say this is first and this is second, right? Unlike an image data, it is always a pixel 0, pixel 1, pixel 2, like that. So how do I pick this data and feed to the neural network? In what order? In any order is fine, because I always append XYZ and the feature, right? So that is so I am always starting with endpoints. That endpoints itself has each point's feature is XYZ, then maybe a three-dimensional feature attached to it. So if you are saying you have to make a system of sorting and then doing it. Maybe yeah. So it can become tricky. It is not still not well represented because there could be, first of all, the acquisition has a sparsity in some area, density in some area. So it is better to design a system that is invariant to this order at all. So that is why people have gone for that robust system. If you want to fix the order from the very input itself, it can get a little tricky because it is not so ordered as in you are presenting an image of a fixed grid dimension, because the sparsity still is not handled here. So So because of these two reasons, the order and the density is not uniform. So because of these reasons, we have dedicated architecture to handle this. So the applications is that once you go take it through this, for every point you get features, just like every pixel you are getting features through a CNN or a transformer. You are going to get features of every point, looking at the neighborhood points if available. The point net presents say 128 dimensional features for every point, and then those features can be used for different purpose. Given a point cloud, I can predict the class of the point cloud, whether it is a mug, it's a table, or a car, and so on. Or given a point in the point cloud, I may want to predict the semantic part of the point, whether it is a wing of an aeroplane or it is the cushion of a chair, and so on. So these are important topics to be solved, because again, when we are talking about robotics and trying to understand a scenario, you get data in form of point cloud, and then you might want to know the semantic label associated with each point, just like you want to know the semantic label associated with each pixel when you're looking at the image, right? So these are important problems to solve in
how do you find the neighborhood of if there is no implicit order?
So there is again people have come up with algorithms which cluster, then yeah, kind of clustering, but then you have to take the k nearest neighbor. Yeah, so again the density and sparsity is a problem, but point net, then one of the how the ordering is handled is because eventually you do a max pooling. So the max pooling is order invariant. So that is how they figure out that's how they solve the ordering part. So there is, of course, there is a neighborhood definition coming, more like a k nearest neighbor, and there is a max pooling that handles the ordering issue to an extent. So so just concluding the discussions on the recognition side, let's move on to the generative side. So if you want to create a point cloud, we have the different ways to create is if you want to create a 3D object, of course the traditional graphics community had created it in a different way, and you see in the recent years neural networks are deployed to create 3D objects. So one of these recent interesting advancements is about neural radiance field. So this is the way where we are implicitly storing a 3D object as the weights in a neural network. So the problem here is we are going to be presented with a few views of a 3D object. So from that limited set of views of a 3D object, a neural network is trained to render any view given any camera angle and direction. So that's the problem. So this is the case where you don't have a generic neural network to be trained to render any view. For an object, you have to first train the neural network with a few set of views, and after the training, very hard training in fact, the neural network can itself imagine how the object would have looked like if you have presented the neural network with a random angle and a random camera position. So that's the problem here. And even the rendering will take time, because the principle by which it is working is it first assumes neural network, if a ray is sent from a specific camera to the 3D world and you sample the points over here, give these points to the neural network. That means I'm giving an XYZ point on this ray. The neural network should predict the RGB value and the opacity value for that point. So that is the way we are formulating the problem. So the inference time, the neural network will send many rays and just samples the points from that ray location and pass it through the neural network, and then predict the RGB and the opacity value, and then eventually you integrate all these predicted values and give how that point would have looked like from the camera viewpoint. So this has to be done for, if you have 1,000,000 pixels, this has to be done 1,000,000 times. That is why this nerve-based rendering does take a lot of advancements have come recently that makes it faster, but it may still take time, maybe running into some minutes to render the 3D views of the object. So that is, but there are, of course, there are more recent methods like 3D Gaussian splatting and all, which has now overtaken the nerve philosophy. So this is the 3D view rendered after passing it through a neural network based prediction. So again, moving ahead, the last slide, while talking about generative AI, we are talking about now how to use text to render a 3D model. That means earlier we are presented the nerve system, neural network with multiple views and ask it to imagine the different views, right? And it can basically predict the RGB value, assuming that inside a ray, what could have been the RGB and the opacity value. Now I am saying that given a text like a DSLR photo of a peacock on a surfboard, I would like to create a 3D model of this text. So how do we do that? So if you look at the generative AI based models, they have been trained on millions or billions of images. And we don't have that much of a luxury with 3D because we have very limited 3D data available, right? So one of these recent works have used nerve to render this model. But where is the ground truth of this coming from? So the ground truth of this is coming from a generative 2D model. So what they have done is they have used a diffusion model, which is a generative model for creating 2D images from text. So a 2D image of a peacock is created using a diffusion model. Now the neural network that we are training is a nerve network here. So the nerve network will be given first presented with a random camera angle and said that using that random camera angle, render a 3D view. Now the nerve is not trained, so it will render something obviously junk. Now, but it will render something from this camera angle. Now I know the camera angle. The camera angle may be from top. So I say that a DSLR photo of a peacock on a surfboard viewed from top. Like that, I can create the text, right? Because I am controlling the camera angle. The nerve is first creating junk, but I am controlling the camera angle. So I ask the 2D diffusion model to create the DSLR photo of a peacock viewed from top, and it will create. Now I will try to train using the nerve output and this model and train the nerve. So from different camera angles, random camera angles used, I will train the nerve and I will create an appropriate text sentence. But these are again not completely controllable because I can maximally say from the top, from the side, from the bottom, from the left, right. Trained, and if you just see their website as the last topic, you can see some of the recent advancements what has been achieved by this team. So I'm just going to this team's website, Dream Fusion, text to 3D using 2D diffusion, and we have so a DSLR photo of a squirrel. If I just click wearing a kimono, so reading a book. So this is the 3D model with the text guidance. So this is the state of the art, and the interesting days are ahead on this topic as well. So generative AI is permeating into the 3D space as well. Yeah, thanks.
I'm curious in that I think that was said on the used to take the on the part of competition, but observation. That is well known for many years now. David Master about the range data from two cameras.
So this is pretty much comes from the structure from motion.
Exactly.
So
But one of the there along the right. So where does it stand in the entire scheme?
So we had the stereo vision where we estimate the R and T between the left and right cameras. But now when it comes to applications, of course, we have the liberty to take more around and get the complete 3D. But stereo vision has limitations from, we are only seeing again, not the complete structure, right? What we call as
Something far from the way that is
I'm not sure how that line of works have evolved. But what you're seeing is not 3D. What we are seeing is 2.5D. We are not. I'm seeing something, but I don't know how much the behind extends, right? So if I'm seeing an object,
there is not sketch of one of these sketches.
what is that?
There is no vision on the one of these sketches, two of these. So you're saying it's only one of these.
So this is typically called as 2.5D, what we see, because we don't know if we are seeing an object. Suppose I'm seeing that cup. I don't know how much the cup extends to the back. But no, still I don't know if with these two eyes I cannot predict what is lying behind, right? How much it's extending. Occlusion, yeah. So structure from motion, the idea is to get the complete 3D structure.
Thank you all for coming. And again, please do come for the next week some others. Thank you.